Welcome to the Deep Dive. Today, we're going under the hood of Ruby 3.4, looking at something that might just make your code run faster without you even noticing how they tackled unnecessary memory allocations.
Yeah, we're drawing heavily from a really insightful talk by Jeremy Evans at Ruby Kaigi. He laid out the whole technical story behind these performance improvements. It's a fascinating look at the nuts and bolts of optimizing a language like Ruby.
Exactly. It's like we're finding these hidden speed bumps that Ruby was hitting internally and seeing how the core team smoothed them out. We'll talk about what these implicit allocations even are, when Ruby makes objects behind the scenes.
Objects it didn't strictly need to create.
Right. And why getting rid of them matters so much for speed. We'll follow their journey of finding these issues in Ruby 3.4 and fixing them. What can we learn about refining a language at this level?
Well, performance work is often detective work, isn't it? It's not just about flashing new features. It's about digging in, finding those small inefficiencies and cleaning them up.
And sometimes the inefficiency you find, well, it turns out you might have put it there yourself.
Huh, exactly. A big starting point for all this was discovering what they called allocation regressions.
Okay, what's that?
It's basically when Ruby starts allocating an object, say an array or a hash, in a situation where a previous version didn't need to allocate one. So performance actually gets worse for that specific code pattern, a step backwards.
And the source had a pretty memorable story about this, right? Jeremy Evans finding his own regressions.
Yeah, it was quite something. He mentioned that while working on this specific allocation problem, he found and fixed 3 separate regressions that he himself had accidentally introduced earlier, all within like a 2-week period.
Wow. That really highlights how complex these internals are, doesn't it?
It really does. You fix something over here, aiming to improve things, and oops, you accidentally make some other, maybe obscure code pattern a bit slower because it now allocates something extra. Everything's connected.
So let's look at some examples he gave. What kind of things caused these regressions? One was about method calls with positional splats, keyword splats, and a block, like def, ma, k, and b, end called with m and proc.
Right.
So in older Ruby versions, that specific call was actually pretty optimized. It didn't create temporary arrays or hashes, but a fix made elsewhere something necessary to get the evaluation order of arguments correct in all cases had the side effect.
Fixing correctness broke an existing optimization.
Precisely. So in Ruby 3, that pattern started allocating an unnecessary array again. The work for 3.4 basically identified that specific regression and fixed the fix, if you will, to restore the allocationless behavior for that pattern.
Okay, got it. What about another one? A method taking a keyword arg called with the keyword splat, def, mk, and of complete 1.
Similar story, actually. In Ruby 3.2, that call was allocationless, but then a bug fix came along related to how keyword splats were handled when the method being called didn't actually define any keyword parameters.
That fix, while needed, accidentally introduced an unnecessary hash allocation for this case, where their method does accept the keyword in Ruby 3 and 3.3.
So another fix causing an unexpected performance hit elsewhere.
Yep. And again, the 3.4 work spotted this regression and eliminated that hash allocation, making it allocationless like it was before. It just shows how careful you have to be with internal changes. Even good fixes can have these ripples.
Finding these regressions, especially your own, must have really driven home the point. You need a system to catch this stuff earlier.
Oh, absolutely. As the speaker pointed out, optimizing code is great, but it's kind of pointless if new changes keep accidentally slowing things down again.
So what was the big idea to prevent this going forward?
Well, it's the classic software solution, really. Tests. But not just any tests. They needed tests that specifically check the allocation behavior of Ruby code.
Tests that literally count how many objects get created. That's pretty specific.
Exactly. They built what they called an allocation test suite. The core concept is pretty straightforward. You write a test for a small snippet of Ruby code, and you assert exactly how many arrays or hashes or maybe other objects Ruby is expected to create implicitly when running that code.
And if a future change to Ruby's internals makes that code snippet allocate more objects than the test expects,
Bang! The test fails. You immediately know you've introduced an allocation regression, and you need to figure out why and fix it before it ships.
that sounds incredibly useful. What were the main benefits they saw from putting this suite in place?
Well, first off, it worked. For the code patterns they wrote tests for, it successfully prevented any new allocation regressions during the 3.4 development cycle. It was like a safety net.
Okay, that's huge.
And it was also apparently super helpful when they were integrating the new Prism parser. They could use these allocation tests to compare Prism against the old parser, parse.he, and make sure Prism wasn't allocating more stuff for the same code before making Prism the default.
Ah, ensuring a major component swap didn't hurt performance silently. Nice.
Yeah. And finally, it gave them a really clear to-do list for optimization. By looking at the tests that, well, initially showed allocations they thought were unnecessary, they had a concrete list of common call patterns that needed work.
The source mentioned a kind of helper for these tests, like check allocations. Can you sketch that out?
Sure, think of it like a function call.
Ooh.
Check allocations, expected arrays, expected hashes, your Ruby code snippet. So for a super simple method call, maybe M1, the test would look like check allocations, 0, M1. 0 arrays, 0 hashes expected.
Makes sense. Nothing complex there.
Right. Now maybe you have a call like MK1. We just talked about that one. In Ruby 3.3, due to that regression, the test would have been check allocation 011, expecting 1 hash.
But didn't you say they fixed that in 3.4?
Exactly. So after the fix in 3.4, they'd update the test to check allocations 00M1. The test always reflects the intended or current correct allocation behavior. If you optimize something, you update the test to expect fewer allocations. The key is having that explicit expectation written down and automatically checked for lots of different patterns.
Okay, I see. The tests codify the allocation budget for different code snippets. Any deviation is a flag.
You got it. And the speaker, Jeremy, felt this test suite was actually his most important contribution to Ruby 3 because it built the foundation. It allowed all the later optimization work to happen with confidence, knowing they weren't accidentally making things worse elsewhere.
So with that safety net built, where did they focus the optimization efforts next? The source dives into optimizing literal arrays like 1, 2, 3.
Right, so things like or1 nage hello.freeze. For these simple cases, especially empty arrays or arrays with only immediately freezable things like numbers and symbols, Ruby was already pretty good, usually just one array object allocated, even for quite large ones.
That seems reasonable. It knows everything up front.
Yeah, but it turned out Ruby 3.3 had some surprising edge cases where it allocated more than one array for literals. A big one was large arrays that contained things that weren't simple literals, like variables or method calls, maybe v1, v2, v257. An array like that with 257 elements would actually cause 3 separate array objects to be created internally in Ruby 3.3.
3 arrays just to make one literal array. Why on earth?
The reason given was technical. It was apparently a strategy to avoid blowing up the VM stack during compilation. If you had a truly massive array literal, the compiler would sort of break it into chunks, maybe 256 elements at a time, compile those, and then compile code to concatenate the chunks.
A safety measure, but with an allocation cost.
Exactly. It was defensive, but those extra arrays for the intermediate chunks in the final concatenation were, unnecessary overhead in most realistic cases.
So how did 3.4 improve that?
They managed to leverage an existing internal mechanism, I think it was called push to array from a previous talk, that lets the compiler generate code to just append elements directly to the first array allocated for the literal. So instead of build chunk, concatenate.
It's just build one array, append, append, append.
Right, much simpler. And it brought these large literal cases down to just a single array allocation.
Makes sense. What other array literals were allocating too much?
Arrays using positional splats. Seems simple, but in Ruby 3.3 that could allocate 4 internal arrays.
4 for just a rel.
Wow. Yeah, it was apparently due to the sequence of internal steps needed. Again, by using better internal instructions that push to array, another one called concat to array, they could streamline the process and get it down to a single array allocation in 3.4. Big improvement.
Definitely. What about keyword splats inside array literals, like A?
That one allocated 3 arrays in Ruby 3.3.
Yeah.
The tricky part here was the keyword splat, specifically the case where H might be an empty hash.
Ah, right. You don't want if H is empty.
Exactly. The existing internal instructions couldn't really handle that efficiently and correctly. Just appending blindly would put an empty hash object into the array if H was empty.
So they needed something smarter for that specific case.
They did. They actually introduced a brand new VM instruction just for this, something like push to array keyword splat. Its whole job is to take the result of the keyword splat expression and append it to the array being built, unless that result is an empty hash, in which case it does nothing.
A dedicated instruction just to handle that pattern correctly and efficiently.
Yep, and that new instruction let them get AT down to a single array allocation too. It also fixed a related bug where A in older Rubies would actually incorrectly include the unto your own array.
So across the board for literal arrays, the goal in 3.4 was basically one array allocation, please.
That seems to be the theme, yeah.
Yeah.
A really nice cleanup for common array construction patterns.
Okay, let's shift gears again. Beyond array literals, the other big focus mentioned was method calls, specifically getting rid of array allocations when you use a positional splat on the caller side,
Right.
like my method summary.
Right. Now, Ruby 3.3 already had some optimization here. There was an internal optimizer pass that could sometimes eliminate the temporary array for the splat, but it was limited.
How so?
It only worked if the splat was followed by very simple things, like only static literal keywords, MAK1, or maybe a single keyword splat, MAK. If you had anything more dynamic after the splat, the optimizer couldn't handle it, and you'd still get the array allocation.
Why couldn't the optimizer handle more complex cases?
Because the optimizer works late in the process, on the compiled instructions. To really know if it's safe to skip the array allocation when there are complex arguments after the splat, Ruby needs to look at the original code structure, the parse tree, before compiling. So the optimization logic had to move.
Move earlier into
Yeah.
the compiler itself.
Exactly, into parse.he, the compiler. It needed to get smarter about splats by looking at the code structure.
What was the main challenge in doing that?
Well, a core issue is just how Ruby's internal method calling machinery works. There's a fundamental constraint. If you have any regular positional arguments that appear after a splat in your call, like MAB, the internal API pretty much requires an array to hold all the positional arguments together.
Ah, okay. The internal API expects a single array for positionals in that case.
Right. And there was an internal flag used to decide whether to create this array, but it wasn't flexible enough. It couldn't properly track the state needed across all the different ways arguments can be combined.
Okay.
You know, splats, keywords, blocks, arguments before and after the splat.
Sounds like the internal tracking wasn't quite up to the task for these complex optimizations.
Pretty much. So they made a significant change to how this state was tracked internally. They changed the flag from a simple integer to a pointer to an integer, which allowed them to manage the do I need to duplicate the splat array state more effectively across the recursive calls the compiler makes.
Okay, so better internal state tracking. How did that help?
It allowed the compiler to adopt a new strategy. Default assumption. Allocate the array for the splat. But before doing that, check the parse tree structure. If the code matches certain specific common patterns where we know there are no positional arguments after the splat, then we could potentially skip the allocation.
So what were those safe patterns they identified in the parse tree?
They found 4 main structures where it might be safe to skip the array allocation for the splat.
Just at the splat itself, like MA,
Yeah.
simplest case.
Makes sense?
2, some regular arguments followed immediately by the splat, like MX, 1XA.
Okay.
3, a splat followed by only literal keywords or a single keyword splat, so MAK1 or MAK.
Right, the cases the old optimizer could handle.
Yeah. And 4, a combination of 2 and 3, regular args, then a splat, then literal keywords or a keyword splat, like MXAK1 or MXAK.
So if the compiler sees code matching one of those 4 shapes, it thinks, okay, maybe I can skip the array for a here.
Exactly, maybe.
Yeah.
Because there's another catch.
Let me guess.
Eh.
Evaluation order.
You got it. Side effects strike again. The problem is, even if the structure looks safe, the content of the arguments that come after the splat might mess things up.
Like your earlier example. The M array key dot Murray dot pop.
Perfect example. The myArray.pop part gets evaluated before Ruby finalizes the arguments for the call to M. If the compiler didn't make a copy of myArray for the splat in this case, the .pop would modify the very same array that Narum's supposed to receive via the splat. Chaos.
Right, so structure isn't enough. You have to check for potential side effects in a later argument.
Precisely. So the improved compiler logic does 2 checks. First, does the parse tree structure match one of those 4 potentially safe patterns? If yes, then it does a second check. It scans the code used for all the arguments after the splat, the keyword values, the keyword splat expression, even the block expression in BLA if there is one.
Looking for what? Method calls.
Yeah, looking for anything unsafe, method calls, certain kinds of constant lookups, anything that could potentially modify state or have side effects during evaluation, if it signs any unsafe code in those later arguments.
Then it has to make the copy of the splat array anyway for safety.
Exactly. Even if the structure looked good, this much more sophisticated check, done right in the compiler using the parse tree, made the old limited optimizer pass completely redundant, so they could just remove it.
Nice. Cleaner and more powerful. You also mentioned a really specific evaluation order issue they found later.
Yeah, a really subtle one. It involved a single keyword splat combined with a block that modifies the hash being splatted. Think myhash.delete.he.
Okay.
If Ruby just passed my hash directly to them without copying it, the block would run, delete the key, and then Room would receive the hash without the key. That's probably not what the programmer expected. You'd expect them to get the hash as it was before the block executed.
Ah, the block side effect happening too early
Right.
relative to the argument passing.
Kind of, yeah. The internal tracking mechanism, that pointer we mentioned, wasn't quite detailed enough for this. It tracked whether the positional splat array needed copying, but not specifically the keyword splat hash in this scenario.
So they needed even more detail in the tracking.
Right. They enhanced it again. Now it tracks two separate things. Should the positional splat array be duplicated? And D, should a single keyword splat hash, specifically in this block interaction case, be duplicated?
Okay, more flags. How did they use that new flag to fix the M hash problem?
When the compiler sees that specific pattern, a single keyword splat hash, and the new flag says, duplicate this keyword splat hash because there's a potentially problematic block, it compiles it differently. Instead of just using H directly, it first generates code to create a new empty hash. Then it evaluates H and merges its contents into the new hash.
Ah, so it explicitly forces a copy just for that single keyword splat hash, but only when that specific side effect risk is detected.
Exactly. That way, the hash that M actually receives is guaranteed to be a fresh copy, safe from any modifications the block might make to the original myhash. A very targeted fix for a very tricky edge case.
That's some impressive dedication to correctness and performance, digging into these really subtle interaction effects. So after all this optimization work in 3.4, are there still places where Ruby implicitly allocates objects during method calls?
Yes, there are still some situations, according to the source, and these seem to be mostly down to fundamental limitations or design choices in Ruby's internal method calling API, which often needs to bundle arguments into a single container, like an array or a hash.
Okay, so what still allocates on the caller side, the code making the call?
Well, the big one is having arguments after a positional splat, like MAB, or using multiple positional splats, MAB. The internal API needs a single array containing all positional arguments to pass along. So the caller has to allocate an array to combine A and B or A and B into one. Fixing that would likely require pretty major changes to Ruby's core argument handling.
Right, the API demands a single container. Makes sense. Anything else on the caller side?
Similar issue with keywords. If you mix literal keywords with a keyword splat, MK1K, or use multiple keyword splats, MK1K2, the caller still needs to allocate a hash. The internal API expects either just literal keywords or a single keyword splat hash, so the caller has to merge them into one hash first. Again, hard to avoid without changing the core API.
Okay, and the third caller case.
That was the positional splat, followed by literal keywords whose values are dynamic, like make some method. Even with the new compiler logic, this pattern currently gets handled internally by turning those dynamic keywords into a kind of keyword splat, which still triggers a hash allocation. The speaker thought this one might be easier to fix eventually than the others, but for now, it still allocates.
Got it. What about allocations that happen on the callee side inside the method being called?
Two main ones related to splats in the method definition. If your method signature includes a named positional splat, like defmargs, and the method itself has to allocate an array to gather up all the positional arguments passed to it and assign them to the args variable.
Needs a container for the gathered arguments.
Exactly. And the source suggests this is probably unavoidable generally. The method needs that array object to work with, maybe pass it around, yield it. Doing complex analysis to avoid it would be really hard, likely needing some kind of complex de-optimization framework.
And I assume it's the same logic for keyword splats in the definition. Decim quarties and...
Yep, same reasoning. The method needs to allocate a hash to collect all the keyword arguments into the core-gigs variable, likely unavoidable for the same reasons.
Okay, and the last unavoidable quarty allocation.
This is when you call a method that only expects positional arguments, but you call it with keywords, like def ma end m n1. In this situation, the callee method m automatically converts the incoming keywords a1 into a hash internally, so it can process them according to Ruby's rules for this situation. That conversion requires allocating a hash on the callee side.
Ah, the method itself does work to handle the wrong kind of arguments, and that work involves an allocation.
Right, so even with all the fantastic work in 3.4, Some implicit allocations remain, largely tied to how Ruby needs to package or collect arguments internally, especially when combining things or handling unexpected argument types.
That makes sense. The focus was on eliminating the unnecessary ones in common patterns, not necessarily achieving zero allocations everywhere, which might be impossible or impractical given Ruby's flexibility.
That's a great way to put it. They targeted the low-hanging fruit and the surprisingly expensive common cases, while acknowledging some allocations are just part of the cost of Ruby's dynamic argument handling system.
What a fascinating deep dive. We went from finding surprising regressions, some self-inflicted even, to building this crucial allocation test suite.
Yeah, that foundation then allowed for really targeted optimizations in literal arrays and those tricky caller-side splats, even dealing with complex evaluation order issues.
And the result for you, the listener using Ruby 3.4, is that a lot of common code patterns just got faster implicitly behind the scenes. Less memory churn, potentially better performance.
It really highlights how much intricate engineering goes into making a high-level, expressive language like Ruby also perform well. It's not magic.
Absolutely. We've seen just how much deep, low-level work in the VM and compiler is needed for these kinds of gains. It makes you think, doesn't it? What does this level of detail reveal about the complexity simmering just below the surface of the Ruby code we write every day?
Or maybe, how do language designers constantly wrestle with that trade-off, balancing powerful, flexible syntax against the internal challenges of optimizing it, especially when fundamental API designs create some of those optimization hurdles?
Definitely food for thought. Thanks for taking this deep dive with us today.
My pleasure. Always fun to explore the internals.